Hi, in this video, we'll learn about normal distribution and what it can tell you about your data. Some of the graphs we've created only visualize one variable, like a box plot or a histogram. This is considered univariate data. Other graphs help visualize and compare two variables, like a scatter plot or a line chart, and this would be bivariate data. In this lesson, we're going to look deeper into univariate data and how we can further analyze a histogram. There are different types of distributions of univariate data when graphed using a histogram. Let's take a look at a few different ways that the frequency of values can be distributed. This graph displays a uniform distribution. All of the values here have a similar frequency across the board. Here, most of the data lies on the left side of the graph, and the tail of the graph is on the right. This is called right-skewed data. This histogram shows the opposite distribution, with the highest distribution on the right side of the graph and the tail on the left. This is considered to be in a left-skewed pattern. This type of distribution is symmetrical with respect to a central or middle point. And this one really doesn't have much of a pattern. This would be considered to have a jumbled distribution. Depending on the type of distributions, we use different techniques to describe the data and understand the likelihood of future data falling within certain ranges. For example, in our skewed distributions, the mean and the median would be great measures to use to help us describe the shape. While for a uniform distribution, knowing the range is very important here because all these values within that range are just about equally likely to occur. In this lesson, we're going to focus on a special case where the data distribution has one peak, meaning there is one most frequently occurring value of data, and the remaining values symmetrically drop off in frequency around that central value. There is no skew left or right in this distribution. We call this distribution a normal distribution, and there are some powerful tools that can help us understand and predict future data. A normal distribution fits a bell-shaped curve. This curve is symmetrical about the data's mean. This bell curve is just a different visual representation of the same type of data, the data that gathers around one central value and drops off as you move left or right. Let's smooth out the curve a bit to explore it further. In a normal distribution, the mean, the median, and the mode are all the same value. 50% of the values are less than the mean, and 50% of the values are greater than the mean. We can also use the spread of the data and the standard deviation to dive more into detail with these percentages. Let's review a bit. When we first looked at histograms, we discussed the measures of spread that were available, such as the variance and the standard deviation. Having a lower standard deviation would inform you that the data had a smaller spread, like in set 1 here. Knowing the spread can help you predict what data values might exist in a future data set of the same kind. Let's take a closer look at set 1. The orange line represents the mean. The purple line to the right is the mean plus 1 standard deviation. This would be 11.1 plus 3.07. which equals 14.17. The purple line to the left is the mean minus 1 standard deviation, which equals 8.03. We can clearly see here that most of the data values lie in between these two purple lines. Now let's do the same with set 2. Here's the mean plus 1 standard deviation, and the mean minus 1 standard deviation. The spread between these standard deviations is much, much wider. This would make it more difficult to predict the value of new incoming data. The percentages in a bell curve can be drilled down even further using these standard deviations. The symbol we see here is the Greek letter sigma, and it represents the standard deviation. In a normal distribution, 68.2% of data will typically lie within the mean and 1 standard deviation, either adding or subtracting that standard deviation. And over 95% of the data lies within 2 standard deviations. These percentages can be split into even more sections and can be used to predict the probability or likelihood of a measurement occurring within a certain range. We can plot a normal distribution curve by including 2 new libraries. NumPy is a Python library used to create complex arrays or lists. It's a very powerful library that can create very large multi-dimensional arrays and includes a large collection of high-level mathematical functions to use on these arrays. SciPy is another Python library used for scientific computing and technical computing. SciPy uses the arrays that NumPy creates. We won't need to use the entire library, so we'll just import the norm function from SciPy. So how do we apply and fit this new normal curve to a dataset? We can start by plotting a histogram of the data. It wouldn't make sense to fit a histogram to a normal curve if the histogram was skewed or had any distribution that was not symmetrical. This dataset here looks good. It seems to be pretty symmetrical around a middle point. A new concept in this lesson is the use of bins when creating a histogram. A bin represents one bar. The default, as shown here, is 10 bins, or 10 bars. This might be an okay choice with this data set, but let's see what happens if we want to separate the data into even more bars, or bins. We can add a parameter. Here, bins equals 25. When we change it to 25 bins, we can see that the bars look much more jumbled around than when we had 10 bins. This is important information to know. Now, the appropriate bin size to use largely depends on the size and spread of your data set. In this case, let's go back and use 10 bins. Another thing we need to change is the way that the data is scaled. A normal distribution uses probabilities and not frequencies like a histogram. If you look closely here, the y-axis represents the frequency. We can change this to represent the distribution by adding in the density parameter. Now the y-axis is in decimal form. These values represent the percentages of the distribution. We'll need to make this change so that we can plot a normal curve, which is also graphed using these values, on the same grid. Before we plot the normal distribution curve, we have to match and fit the x-axis as well. Remember that the normal curve is graphed using the mean and the standard deviations. We can find these values by using functions. The mean function and the standard deviation function. These are applied on our data. Then what we can do is set the minimum x value to the mean minus 3 standard deviations, just like a normal curve, and the maximum x values to be the mean plus 3 standard deviations. NumPy has a function which will take these two values and separate them evenly to form the x-axis. Take a look that this does not say line space, but it says LIN space. Now that we have the x-axis set up, we can use these values to calculate what's called a probability density function, or PDF. A PDF is used to determine the exact probabilities of values when these values follow a normal distribution. This function can be used to find the y value that corresponds to each x value based on the normal distribution. Each x value will correspond to a spot on the graph of the normal curve. So we have our x values from earlier. We can now use the norm.pdf function from the SciPy library to calculate the normal distribution. This function takes the x values, the mean, and the standard deviation. Now that we have x and y, we can plot the normal curve. There it is. SciPy includes a cumulative density function as well that we may find useful in our data analysis. This function adds up all of the probabilities that come before a value. Let's take a look at how we can use this function. Let's start with an x value of 50. The PDF would give us the point on the curve that corresponds with this value. But if we use the norm.cdf function, as shown, it will tell us that about 85% of scores are less than 50. Well, that's definitely helpful. We can also determine how many scores are more than 50. Since this is a percentage, we can simply subtract 85% from 100%. We can also do this calculation within the code. This time we'll include 1 minus the norm.cdf, and this will let us know that about 15% of data will be greater than 50. All right, well now it's your turn to dive deeper and explore more about these concepts.